My name is Jeremy Mason. I'm going to talk to you today about the structure of materials, which is a very broad subject. Bob McPherson and David Srolovitz, who's over in Singapore at the moment, and also Emmanuel Lazar, and I are working on this project together. Mostly interested in metals and ceramics. So if you take a metal or a ceramic and you just cut it, you cut a surface, make sure it's to a certain degree smooth, and then apply some chemical etchant to it, like an acid, you're going to see something like this. These are actually two microstructures. These are both steel. They may be electronic grade steel. And so you see that there's some variation in these structures just in terms of the size, but if you look at them topologically, they look fairly similar. So we're interested in describing these things. This is a simulated structure that's come out of some numerical code that we're running. And you see superficially that these look pretty close. So we're really interested in describing these. We're interested in understanding these structures and being able to manipulate them in order to engineer better materials. And this is the model system that we're working with. So to tell you a little more about this model system, we work exclusively in 2D at the moment. Emmanuel's he's just got some 3D code working, which we're very interested in. But I'm presenting on the 2D case. So in the 2D case, this is a cellular complex. Two cells come together at an interface that I'm going to call an edge. Three edges meet at a vertex. So the graph formed by the edges is trivalent. We actually discretize this. These are straight line segments. We break every one of the edge down into these straight line segments in order to approximate curvature. All of the boundaries, all of the edges in a real system, they're associated with some excess energy per unit area, which I'm going to refer to as gamma. It has the same dimensions and actually is numerically equivalent to a line tension in the two-dimensional case. What this does is it drives the system to minimize its total boundary length in 3D, or its total boundary area in 3D, or total boundary length in 2 dimensions. It's always trying to minimize its energy. So what this is going to do is it's going to flow in such a way as to achieve that. Practically speaking, this means it goes by mean curvature flow. So locally what you do is you look at, you approximate the curvature of this. These are obviously straight line segments, so you're looking at the turning angle. But you can imagine every point on one of these edges moving toward the center of curvature at a rate proportional to the curvature locally. And so we just let it evolve by that.
Why do we have many parts on some line and few parts?
So this is a numerical trick that we did. We actually run these simulations sometimes with tens of millions of grains. So these are really tremendous systems. We're doing lots of numerical calculations. This is just, it's a time-saving step. Where the curvature is very low, where the boundaries are very flat, we put in just as few points as we can while adequately capturing that curvature. Where it's highly curved, we break it up a lot more because we want to have this as accurate as possible while still running efficiently. So there's some consequences of this. It's actually not too difficult to see that from mean curvature flow and from the existence of this boundary energy, we require that the angles around these triple points to all converge to 2 pi over 3. Another way of looking at that is just saying, well, the boundary energy is equivalent to a line tension, and so we require that the region around this be in mechanical equilibrium. You can only do that if you have 3 equal forces in this kind of triangle, where there's 120 degrees between those. So this is a very natural consequence. This is actually also a natural consequence, but you need to think about it a little more. This is referred to as the von Neumann-Mullins law. It expresses the fact that in these systems, if you allow them to evolve according to this rule, the rate of change of the area of one of the cells in time is proportional, these are just some proportionality constants, to the number of sides of the grain minus 6, which is a striking result, but it's true. So there's only 3 kinds of topological events, we believe, and so does the majority of the material science community, that happen in these systems under those constraints and under that flow that I described in the previous slide. One of these is the disappearance of a digon. Under certain circumstances, it happens more frequently than you would imagine. You have an edge which is decorated by a diagon, and so this simply collapses, just disappears. So that's one kind of topological event that we can see in these systems. Another one, which this was actually suspected to not happen for many, many years. It's now observed, it's now very clear that this does take place. For a long time, it was thought that this was the mechanism by which grains disappear. This was the only one, where you have three edges coming together and you have a trigon there, and then it vanishes just down to a point.
So when you say the first one has been found, computationally or in reality?
Well, so in reality, most of the systems that we look at are three-dimensional, and so we look at two-dimensional sections of these, and you can watch those evolve, but because you work in 3 dimensions, because you're working with a 3-cell complex, a lot of the rules that I'm telling you don't work. If you look at just an arbitrary section of a 3-cell complex where you have this constraint that the surfaces come together at dihedral angles of 2 pi over 3, depending on the section, that's not satisfied in 2 dimensions. So a lot of what I'm telling you is just it's not applicable. So we see this computationally. We see this in expressly 2-dimensional systems.
So what kind of two-dimensional system are the bubbles or are they?
Yeah, so for example, I'm going to get to that. A good approximation to this, you take 2 sheets of glass and put bubbles in there so that the diameter of the bubbles is always greater than the separation between the glass plates. And there's various mechanical, there's various other systems that we can do to approximate that. So you have disappearance of trigons in these expressly 2D systems. You also have edge flips. And so what I'm going to do is I'm going to show you a movie of one of these things evolving. And you can keep an eye out for these 3 kinds of topological events. I'm going to warn you that the digons, please excuse the fact that it's jerking a little bit. That's not actually happening in the system. That's because of the way I rendered it. You'll see digons occasionally, but they disappear extraordinarily quickly. The rate of change of the area is proportional to n minus 6. So if it's 6-sided, it stays fixed. 2-sided, they shrink the fastest of any possible grains. You'll occasionally see them, if you have something like, let me see, something like this. It'll pinch off there, and then sometimes it'll pinch off on the other side and have enough area left over, it'll be abandoned in the middle of an edge. They're extraordinarily hard to catch in this kind of picture. If you look at still images, you can pick them out with not too much difficulty. So that's one thing I want to point out. Another is, if you look at this final image, it's about to get there, this structure looks completely different than the way it started. It actually started from a Voronoi tessellation using randomly distributed, using points in the plane. These are just distributed according to a Poisson distribution. It's a uniform distribution. The end result was completely different.
I don't understand why it's the end.
I'm sorry?
It's the end because it's now.
Well, it's the end because the video ended. I'm going to get to that. Yeah. Nothing special there. Okay. So here's a second model system. This is actually a foam. We also model soap foams. So soap foams, it's essentially identical. You'll notice that there's no subdivisions of the edges. That's because there's an additional constraint in the case of soap foams. As far as I can tell, there's only one additional constraint, and it's that the edges be constant curvature. So I didn't point it out in the last video. Maybe I should have. It's occasionally possible to have the curvature of a single boundary change sign as you progress along that boundary in the case of grain growth. Expressly forbidden in this case. In every moment of time, this system is entirely in mechanical equilibrium. And so I can show this to you also. It looks completely different. This is actually the same initial configuration. It's the same Voronoi tessellation. But it works now under the constraint that all the boundaries are arcs of circles, and all the angles are 120 degrees. That one additional constraint.
But what is the evolution?
I'm sorry? Still mean curvature flow. Everything else is identical.
How can you adjust the constraint?
Wait, it's not quite accurate.
It's not quite accurate.
Curvature flow,
Okay.
But the von Neumann relation.
Sure.
holds.
Sure. Yeah.
It turns out that it's uniquely specified by the 120 degrees von Neumann relation and the arc of circle.
Yeah.
Does
As
it mean that fixing equal curvature is very fast?
Yes.
Yeah, so in the case of this kind of foam, there's actually 2 time scales. There's one time scale associated with diffusion of gas between the bubbles, which follows the von Neumann relation. And there's another one associated with the redistribution of gas within a bubble, which we approximate as instantaneous, which is why whenever you have a topological event, there's this kind of discontinuous change in the geometry. But this is in fact necessary in order to satisfy this constraint that all the boundaries be arcs of circles. And this is in fact what these systems look like.
But when you would violate, you make a jump.
Absolutely, yeah. So that you can think about these as line tensions, and every one of the bubbles is having a pressure. And if you do that, then I can say that in every moment the system is in mechanical equilibrium.
As you look at this picture, it looks like the density is going to zero fairly quickly.
Well, I'm not scaling time linearly, right? And we are working with finite systems, so what you're seeing is coarsening. That happens in physical systems. It also happens, in bubbles in your beer or soap froths in your sink. Same thing. If you sit and watch them for hours, you'll see a similar kind of process. So here's our conjecture. We can't prove this. We have no idea how to go about proving this. But one of the things that we see is that for almost any initial condition, meaning the cases where this is not true look like they're a set of measure 0, if we apply, you have to qualify the statement with Bob's comment, mean curvature flow eventually results in some kind of steady state.
Can you define steady state?
Not precisely. That's part of the issue. So we start with this structure. This is a Voronoi tessellation from points taken from a uniform distribution. This is actually, we work on the torus. We work on the 2 torus to deal with the boundary conditions.
So you must be renormalizing also, because your bubbles were getting bigger, and if you want some steady state, you probably are...
That's assumed. That's assumed that we're rescaling space. So if you start...
Do you have to rescale time also, so that the evolution becomes
Yes.
similar looking?
Yes. Yeah, that's exactly right. So if you start off with some structure that has n cells on the 2 torus, this is actually expressly what I'm doing here. So I took this structure and I evolved it so only 1/4 of the number of cells remained, and then I rescaled it so that the average cell size was identical. So that's 1/4. This is actually 1/100th. We started this out with 10 million cells. So this is what, 2,500,000, and now we're down to about 100,000, and this is again not precise at all. But you look at these two, and you don't see very much difference. And we've tried to quantify this. We've thought of all kinds of different statistical measures. Every one that we see, they all stabilize. They all reach some steady state. Don't really know why. We'd love to. We'd love to figure out why. Here's the second part of the conjecture. For almost all initial conditions where we have a steady state, it looks like the steady state of one is indistinguishable from all the others. So here's 2 initial conditions. This is a Voronoi tessellation from Poisson distributed points. This is constructed in a different way. That's not terribly important. What is important is that if you let these evolve long enough, you end up with structures that look the same. And indeed, all the statistics that we can think of, if we measure them, they all come out to be identical. This is really striking. Don't know why. Don't know how to prove it. How much time do I have? Am I done? Few minutes, okay. So here's one of the ways that we're trying to deal with this. Bob is interested in topology. So so what we do is we put down some additional structure. We put down flags. So a flag I'm going to associate with a particular cell. This flag I'm going to associate with this cell, with this edge, and with that vertex. And I'm going to represent that by some black dot, which is within the cell and near the edge and near the vertex. Right? So we do this through the whole structure. The next thing that you do is you say, well, this one, this flag, it differs from that one only by the edge with which it's associated. It differs by this one only from the vertex with which it's associated, and by this one only with the cell. So I can put down some operations that carry a flag to those 3 neighbors. Right? And I've just colored those according to 3 different colors. It turns out that these operations, these 3 operations, are the generators for a Coxeter group with relations that you can see from this just imposed by the geometry. You have some circuit here, so 2 purples and 2 blues. And you have some circuit here, which is 3 yellows and 3 blues. But that's actually not important. It's not so important that it's a Coxeter group. What's important is that we can pick some base flag, and then we can start asking questions about the stabilizer. We look at the elements of this which return that base flag to itself, and that will tell us something about the structure. In fact, I claim that that completely characterizes the topology of the system. If you pick a base flag and you know the stabilizer, you know everything about the topology, and I'm going to prove that to you by this series of images. You take some base flag, you take an element of the stabilizer. Say that it's one component that runs around the interior of this polygon. Well, now that you have this element, it was one of the shorter elements, you can start building it up. You can start taking longer elements, and you realize, oh, if this is here, then this longer element, which runs around the interior of both of these, implies the existence of this cell. And you can repeat this process and gradually build up the structure. So this is great, except we have an assumption of spatial homogeneity. There's no particular spot in the structure that's special. So how do we incorporate that? Well, we incorporate that by doing the following. Rather than picking a particular base flag and looking at that stabilizer, we pick a base flag at random, we take the stabilizer, we throw away the base flag and keep the stabilizer. We pick another base flag and do the same thing. So now we have this collection of stabilizers. And what we do is we look at statistics about the elements of those stabilizers. And from that, we can learn something about the kinds of structures we see. So here's a game. This is the same picture I showed you on the first slide. What structures do you think are most likely?
Hexagon?
Sorry?
Hexagon?
No. That's what we thought too, but I'm going to show you the top 10 most frequent structures. Nowhere in there. Hexagon's around 30. Any others? Nope. That's even lower. It's these guys, which is really strange. Hexagons are the most frequent. 5-gons are the next most frequent. 7-gons are the next most frequent. And you see those appearing in these. So this is the most frequent. It runs down in that direction and then down in this direction. So you see hexagons and pentagons. And then 7-gons, heptagons, I guess, and hexagons. And they occur in various pairs. Here's 2 hexagons. But there's this amazing progression here. A hexagon and a pentagon, same ones, but with one additional side. Here's a 7-gon and a 6-gon, the same pair, but with one additional side. Then you have 6 and 6, and then a 6 and 6 with one additional side. We don't know why. This is actually, these statistics are captured from the steady state, the apparent steady state. We don't know why, we don't know what this means about it, and there see some very strange things that seem to not fit. Don't understand.
This on each steady state.
Yes, each steady state, same 10. Yeah, out to 3 or 4 decimal places. We're measuring the frequency of these things. Don't understand it. So lots of open questions. That's all I have to say.